he finished in 2004 doing his thesis with Sol Rappaport. Then he moved as a postdoc to Northwestern, where we met and worked at the same place as postdocs. And now he's a Chandler Fellow, and he's moving to KTP this fall. And today he's going to talk us about X-ray binaries and the cluster dynamics.
Hi, well, thanks for having me. It's fun to be here. I just found out today that all the summer undergrad students have to go to every seminar. Is that true? And I apologize in advance, but I'll try to keep it not too boring. So as Natasha said, I'm going to talk about X-ray binaries and in particular what we can learn about the dynamical states of globular clusters by observing their numbers. So I really only want to make one point in this talk, and that is that by looking at the numbers of X-ray binaries in globular clusters, we can determine something about their dynamical states. And in particular, it turns out that their evolutionary status is, well, I shouldn't say younger. So the ages are not in dispute at all, but their evolutionary state is earlier than we had thought before. So they seem to be less mature than we thought. And that's really the only point I want to make, and I'll get to that now. So there are many objects in the sky that when looked at in different wavelengths look very different. Globular clusters are no exception to this rule. This is NGC 7099, and I apologize, this projector is not the brightest. But so this is an optical image of NGC 7099 right here. And you can see it's very centrally concentrated. There are tons of stars. And then this right here is an X-ray image. And it's kind of hard to tell, but it's all black except for a few bright spots. So what you have is just a few bright X-ray sources in the dense core. And if you repeat this exercise for all the globular clusters in our galaxy, you find that they're overabundant in these bright X-ray sources. And when I say overabundant, I mean per unit mass compared to the disk population of the galaxy. And this is something that was known about for at least 30 years, going back to the work of Clark and Katz in 1975. And it's also true when you look down to lower X-ray luminosities. And when you do that, you see not only LMXBs, these low-mass X-ray binaries, but also cataclysmic variables, which are the analogs of LMXBs, just with white dwarf accretors, millisecond pulsars, and active main sequence binaries. And it was quickly realized that this overabundance should be caused by the very high rate of dynamical encounters in the dense cores of these clusters. And this goes back to the work of Verbund and Hutt in 1987. They looked at the densities and looked at the stellar interaction rate and saw that it was very high. But it was only recently that this was quantitatively confirmed. And this is going back to 2003 by the work of Dave Pooley et al. And what they did was they looked at a bunch of globular clusters in our galaxy. And they looked down to a limiting X-ray luminosity of 4 times 10 to the 30 ergs per second. And what they found was that the number of sources in a cluster scales pretty well with something they call gamma, capital gamma, which is just a measure of the encounter frequency, the interaction rate in the core of the cluster. And this is what I have plotted right here. This is the number of the X-ray sources. And this is this encounter frequency, gamma. And you can see for most of them, over a few orders of magnitude, there's a very nice correlation. It's actually more than 2 orders of magnitude. Very nice correlation, except there are a few outliers. And these outliers right here are actually going to be the main point of my talk. But let's just ignore them for now. So if you just ignore those, that's a very good correlation. That tells you that, in fact, yes, these X-ray sources are mostly dynamically produced. So this plot right here shows all X-ray sources greater than 10 to the 30 ergs per second, roughly. The dimmer sources in that group are the CVs. And the question there is, are those also dynamically produced? One of the things that Dave Pooley found in his study was that, so there's a clear correlation between the number of sources and this encounter frequency, but there's also a correlation between the encounter frequency and the mass of the cluster. So there's a little bit of degeneracy there. And in some cases, it's not explicitly clear if the sources are dynamically produced or you just see more of them because the cluster is more massive. So what they did in a paper in 2006, Dave Pooley and Pete Hutt, was they worked in specific units. They just divided everything by the mass of the cluster. And they looked at the number per cluster mass versus the encounter frequency per cluster mass. And if all of these CVs, so this is mostly CVs now that they've been able to isolate from the X-ray color magnitude diagram. If they were not dynamically produced, then the number per unit cluster mass would just be a straight line, right? But clearly, as you increase the encounter frequency, it goes up. So that tells you that, yes, also the CVs are dynamically produced. And this is something that wasn't really expected going back to the work of the 70s.
Kind of probability for this little gamma probability for a star to encounter another one?
Yes, that's right. Yeah, I'm going to actually...
Any given star in this cluster.
Yes, I'm going to calculate this later on in the talk. But it's basically an n sigma v type argument where you look at things smacking into each other, basically. That's right. So why is this interesting, you might ask? Well, it's interesting because we see a lot of these X-ray sources, but so it's sort of inherently interesting. But another reason is that, in some other early type galaxies that we look at, we see a lot of LMXBs. And it was proposed back in 1984 by Josh Grinley that maybe all the LMXBs that we see were formed in globular clusters, because they're clearly factories for making these things. And there are a few ways you can assess this hypothesis. One of them is to look at the number of LMXBs that you see, and this is actually proxied here by the X-ray luminosity, and the number of globular clusters in a given galaxy. And you work in specific units. So this is L optical of whatever elliptical galaxy you're looking at, but you can take that as a proxy for mass. So you're basically looking at the specific number per galaxy mass, right? And you look at the correlation between these two properties, the number of clusters and the number of X-ray sources. And if you extrapolate down to 0 clusters, if you see some X-ray sources, it means that there are some that are not just formed in clusters, right? There's some contribution from the field. And this is actually what a whole bunch of people found back in 2005 and 2006. They found that they're not all formed in globular clusters. Another way of looking at it is looking at the concentration, the radial concentration in the host galaxy of the LMXBs and the globular clusters. And oh, I actually have a typo there. So what they found is that the LMXBs, oh, that's strange. So what they found is they looked at the LMXBs and they looked at the globular clusters, right? And they found that they had different radial distributions, right? So that tells you that maybe they don't all form from the globular clusters. And this was Arnav Kundu in 2007. And yet another way to look at this is if you look at the X-ray luminosity function, right, in a galaxy. And what you see, if you look at the field and globular cluster LMXB sources, you can actually pick them out based on their position in the sky. You find that the X-ray luminosity functions differ slightly. And this is Pepe Fabiano's work from 2008. So these are just three things, three different types of studies that suggest that, in fact, there is a cluster formation channel for these LMXBs, but also they form in the field. The only contrary piece of work goes back to Humphrey and Buat in 2006. And what they found, in fact, was that the spatial distribution of the LMXBs is similar to the red globular clusters. And also that this proportionality right here, when you take it down to 0 globular clusters, gives you 0 LMXBs. So I think it's something that's not quite settled. It's something that we'd like to understand.
Quick question.
Yeah.
Are there LMXBs in the Milky Way?
Oh, yeah, yeah.
That aren't in globular clusters? I mean, just in the disk and the bulge?
Yeah, there's some in the field, yeah.
So, so if they had seen LMXBs in the Milky Way that were in globular clusters, why would you think they wouldn't be LMXBs in other galaxies that weren't in globular clusters?
Well, we don't know the origin of LMXBs in our galaxies. We don't know where they've been created instead, because it's very difficult to produce them initially from a primordial binder. So the idea was that even in our galaxy they could be produced by global clusters, which we just don't see now.
That somehow made their way into the disk and globular clusters gone?
Yes.
Okay.
They're not in the disk. They're not necessarily in the young population.
They're not necessarily in the normal local population.
Not necessarily in the young population.
Okay. Thanks, Natasha. What's that?
They're fast moving. Local objects.
You cannot exclude the possibility that they will become some global clusters just being exposed by massive release.
So the kinematics are not known at all. Like these systems, field population, this population, this is not known at all.
Well, it's not that you can exclude it. They exclude possibility to be in global clusters.
Pretty easy to fully tell this, right? This populations are moving around 20 kilometers per second in a disk, and the other populations moving around randomly. Yeah, how's this not known?
So why don't I just move on then? Thanks for thanks for answering, Natasha. So let me now switch gears a little bit. And instead of talking about observations, I want to talk a bit about some theory that's been done. This is work that Natasha's done that I'm going to highlight in these next two slides. And what she's done is she's done Monte-Carlo simulations to look at the formation and evolution of X-ray binaries, and all kinds of binaries, actually, in star clusters. And what she finds for the CVs is almost exactly what Dave Pooley finds in his observations, and that is that the formation rate of CVs from dynamical channels is about 3 times higher than it is if you don't have any dynamics. In other words, if you're in the field. And these formation mechanisms are predominantly exchange and binary interaction. So the idea here is you have some binary, and because it's big, it has a big cross-section to interact with stuff. And when another star comes along, the thing, when they get close enough, the thing acts like a very small, n equals 3 star cluster, and one of the objects gets kicked out. And in an exchange, the star that was coming in exchanges into the binary, and one of the original members of the binary gets kicked out. So that's one of the dominant formation channels. Another is physical collisions between a main sequence and a red giant star. They literally smack into each other, and you strip off the the envelope of the red giant. One of the interesting things that comes out of this is that for CVs at least, and this is not clear for LMXPs, for CVs, the types, so field versus dynamically formed CVs differ in their properties, and they differ in their X-ray luminosity and the rate at which they have dwarf nova outbursts. Now, moving on to LMXBs, Natasha, just like what the observers find, she finds a very strong correlation between the number of these X-ray binaries, these LMXBs, and this cluster encounter frequency. So that's good. Another thing that she finds is that in order to keep the number of neutron stars that we see now, it must be that they predominantly form from electron capture supernova as opposed to standard core collapse supernova. And the reason for this is just that you have a smaller kick speed when they're formed. I'm not an expert on electron capture supernova, so you could ask Natasha if you're interested. She also finds that the number of quiescent LMXB sources should not depend on the metallicity. And this is in contrast to the bright LMXBs. And in fact, this is exactly what's seen in the observations. And I'll just skip that last point here. So I hope I've given you some background and some motivation for why we're interested in this sort of thing. So let's go back to this Dave Pooley plot right here. So again, this is the number of X-ray sources in a given cluster, and this is the encounter frequency, the rate of things smacking into each other. And I don't literally mean smacking, I just mean interacting in some way gravitationally at the center of the cluster. And there's a nice correlation, but there are 3 outliers. And the question is, why are these 3 so far above this nice correlation? And it ranges from a factor of, say, 2 all the way up to 20 right here. This is above by a factor of 20, and it's significant. The error bars don't overlap with this curve right here. So the question is, what's going on? Well, could it be that there's some, could it be due to the correlation between the number of sources and the metallicity that people see? If you look at a lot of elliptical galaxies, what you see is that the number of bright LMXBs tends to scale with the metallicity and with the metallicity of the cluster. And it turns out that the cluster metallicity distribution is pretty much bimodal. So the more metal-rich clusters tend to have, turns out, a factor of 3 more of these LMXBs than the metal-poor clusters. So could it be due to that? Well, it's not so clear because these LMXBs that have been looked at in the study are the very, very bright ones, right? Because it's for a galaxy that's far away. If you do the same exercise, but for our own galaxy, including low luminosity X-ray sources, it's not clear that this correlation exists. But just assume that it does. If it does, then the question is, what is the metallicity of these 3 outlying clusters? Well, it turns out that 6397 and 7099, and let me just go back, that's this one right here and this one right here, are the 2 most metal poor of the whole sample. So if anything, if that correlation were true, they should be below this curve. And Terzen-1 has a metallicity of minus 1.3, but the whole rest of the sample ranges from minus 0.3 to minus 1.8 or so. So that's out the window. We can't explain it by this correlation that people observe. Well, could they be primordial? So I mentioned before that if you have just a lot of mass, you may have more of these X-ray sources, right? So this Pooley sample, as I mentioned before, showed this correlation between the encounter frequency and the cluster mass. So how do we know that they're not primordial? Well, if you look at the masses of the clusters, so if you assume that all the X-ray sources that form in a cluster are primordial, so there's no dynamics at all, it's independent of the central density, what you would expect then is that this cluster would have the same number of sources as this one, which would have slightly more than this one, which would be more than this, and this one would have more than Terzen-1. In other words, all of these, say these 6 right here from 6752 on down, would be monotonically decreasing in the number of sources. So that explanation clearly doesn't work. So the question is, what's going on? Why do these things have so many more sources? And I apologize for laboring this point, but I want to make the point clear. Well, if you take all the sources in the sample, all the clusters in the sample, and you do this game that you learned when you were maybe 5 or 6 years old, and you say which of these is not like the other, well, it turns out that these outliers right here are all what observers call core collapse clusters, and I'll talk about what that means in a second. while the rest of them are not core collapsed. But what is the definition of core collapse? Well, it's really just an observational definition. And all it says is that if you look down to your limiting resolution of your telescope, you see that the surface brightness density profile is continually increasing with decreasing radius. And of course, this is dependent. This definition depends on how far away the cluster is, right, and exactly what instrument you're using. And it's not clear how this relates to the evolutionary state of a cluster, but I'll get to that shortly. And if just some numbers for you, that of the whole galactic globular cluster sample, about 20% are called core collapsed, while the other 80% are not. So, okay, so observers see that these three outlying clusters have really small cores, right? They call them core collapsed, while the rest don't. But what does this mean? So it's good to go back and think about the evolution of a star cluster. And a star cluster, you know, it's a balanced self-gravitating system, which is a lot like a star, and its evolution is a lot like a star. And it goes through typically 3 phases of evolution. So this is time on this axis right here, and I just want you to focus on this middle curve. This is the core radius divided, just the core radius. It's actually divided by some scale. The core radius of the cluster. And when the cluster initially forms, the core radius shrinks and shrinks, just like a pre-made sequence star does. And eventually the core gets small enough and the density high enough so that binary stars that are there from the very beginning, they start interacting with other stars. And when they do that, they're like an energy source, just the same way that hydrogen is an energy source in a star. And it keeps keeps the core radius from collapsing. And this is equivalent to the main sequence phase of a star. And that's this really long phase right here. Right? We call it binary burning because it's burning a fuel, and binary because binaries are the fuel. And eventually, after all your binaries are exhausted, what happens is the core just really decreases in size. It goes through what theorists traditionally call a core collapse, but now we'll call it deep core collapse. It goes into deep core collapse and goes through this series of what are known as gravithermal oscillations. And if you ask any globular cluster theorist, well, if you asked them a year ago, where would you expect to see most globular clusters, what phase? They would say, well, probably here in this binary burning phase. Why? Well, because this phase is extremely long-lived, right? And if you just pick at random anywhere along this plot, so ignoring these for now because they happen well into the future. If you pick any random point, probably most of the time you'll pick it on this binary burning phase. So the binary burning phase has been of intense study in globular cluster, in the globular cluster theory world. We've been studying it for a long time, but it's only recently that people really settled on what the equilibrium size is of the core in this binary burning phase. It sounds kind of crazy, right? Because it's just F equals ma and Newton's laws. Why haven't people figured this out before? Well, the n-body problem is a very difficult one, especially as you get up to large n. But as I was saying, in the last year or two, there's 2 independent, very different numerical methods, one of which is n-body, and the other is something called the Monte-Carlo code, which just solves a problem in energy and angular momentum space. They finally agree, and they agree extremely well on what the value of the core radius, well, we usually divide it by the half mass radius just for scale. They agree finally on what the size of this radius is in the binary burning phase. And
not make new binaries to burn?
so you can make binaries only by 3-body processes. Okay, so you can make them by 2-body processes via tidal capture. So what happens is you get 2 stars that pass close enough that they dissipate some energy and become bound. But the parameter space for that is really small. And most of the time what happens is the stars either get shredded or merge, right? So if you just exclude that, and most people think that really doesn't happen in nature, if you exclude that, the only way to form them is by a 3-body process. So you get 3 stars that get close enough together where one of them takes away enough energy for the other 2 to remain bound. And that is, the rate of that scales with density cubed, right? But all these other processes that I've been talking about so far scale as density squared. So in other words, what happens is the density never gets high enough to form those 3-body binaries, unless you get down here, and that's exactly what's responsible for these oscillations. So you run out of binaries, your density gets really, really high, right? And you form this 3-body binary, and then this is what powers this expansion and these oscillations.
So that it's a discrete steps like that suggests, I mean, each one of these kind of you make a new generation of binary that fuels another binary burning stage or something?
You make one right here.
Oh, those are individual binaries.
No, this is the core of the cluster. So here, let me explain. So the density gets really high. You make one binary. And it turns out this collapse phase is actually an instability But when you form a binary and it generates energy, the expansion is also an instability, right? Which is weird, but that's what happens. So the thing expands, it expands too much, and eventually contracts again.
So each one of those little spikes is supposed to correspond to the formation
Of one binary. Yeah,
Okay.
yeah.
That's cool.
It's wacky. But you never see it in nature because this happens way in the future.
Oh, yeah.
Yeah, yeah. So let me just get back here. So, right, so as I was saying, we finally agree, the N-body and the Monte-Carlo people, on what the size of the core radius is in the binary burning phase. And what we find is something rather shocking, and that is, if you look at most globular clusters in our galaxy, their core radii are 10 times bigger than what we expect from the theory, right? And that's bad. But let me just try to convince you that that this is probably correct, okay? So let me just show you how different these codes are. So in N-body, what do? It's exactly what you expect. You integrate F equals ma, and you write down the Newtonian force, and it makes no simplifying assumptions. And these binary interactions that power the binary burning phase, those are, of course, in there de facto, right? You don't have to worry about them at all. But it's very computationally expensive. So you need special purpose hardware. You've probably heard about these grapes. These are accelerator boards that calculate the 1/r² force for N particles. And then on the other hand, you have the code that I've been working with, which is the Monte-Carlo code, where we treat the evolution in an orbit averaged way. So we can take much, much bigger time steps, because we only worry about what happens over many orbits. So we look really at the energy of each orbit and its angular momentum and watch them slowly diffuse in phase space. So because the time scale is so long, we can do really large n. So these guys are limited to about 10 to the 5 for no binaries. And if they include binaries, they can maybe do 10 to the 4. But clusters in the galaxy, may have started with 1 million stars, right? And many of them have 10 to the 5 and binaries. So we can do the large n. There are some assumptions that we make, but they're pretty reasonable. One is real equilibrium. We don't see any clusters that are out of this equilibrium. And spherical symmetry. Most clusters that we see are pretty darn spherical. And the strong interactions, though, these binary interactions that I mentioned before, we have to treat those specially. And the way we do this is every time one of these happens, we let an n-body integrator integrate just the small n interaction and take the results and plug them back into the code. And this is a comparison that we have right here. So this is the core radius divided by the half mass radius as a function of time. And this red line is an n-body calculation, and the black one is from our Monte-Carlo code. And this time scale of this initial collapse, they agree pretty well. And in this binary burning phase, it looks like they differ, and they do, but that's only because of a scaling with n. So we understand, yes? Yeah, that's half mass relaxation time. So when you first start looking at the cluster, so you can assume when it's formed, you calculate the relaxation time at the half mass. This can be 1 billion years, say. So this is extremely long evolution, right? This is 20 Hubble times, right? So the value of RC over H in this phase, it differs between the two, but that's only because of the scaling with n. So this n-body calculation uses 16,000 stars, while ours used 100,000. And if you plug in, so we know pretty much from theory how this should scale with n. So if you plug that in, these two curves actually overlap. So this is very significant that these two very different methods agree. And ours. Yes, it does. And we started with the same. I think it was 10% here, something like that.
So that's fairly high.
Depending on who's if you ask Natasha, she'll say most clusters start with 100% binaries. Yeah. For the n-body people, 10% is pretty computationally expensive. So for them, it's high. Yeah. Observationally, what we see for most clusters in the core ranges from a few percent to tens of percent, something like that. Of course, for open clusters, it's 50 or more.
I know, because
yeah.
these NGC 6397, I just heard at almost 1 or 2% at the half mass rate. Very few.
Yeah, that's actually, so I think this takes in the new revised, so this is last year. One of Harvey Richards' students actually calculated, yeah. In the core, it could be, I guess it's like 12% or something like this. So that's this point right here for 6397, yeah. So let me just describe what this plot is. So I said there's a big discrepancy between theory and observations. It's bad. This is core divided by half mass radius. Again, this is central binary refraction. And this curve right here is this new understanding that we have from simulations about what the value of the core radius divided by half mass radius is in the binary burning phase. And then I have a bunch of points here. That show what the observed values are for RC over RH, and what the observed value is for the core binary fraction. So we haven't observed the core binary fraction for all clusters, but we have it for some. And as you can see, there's a big discrepancy right here, right? If you expect most clusters to be in the binary burning phase, right, then they should be on this curve, but they're above by a factor of 10, at least. So it's bad. Yeah, for some clusters. It's not disallowed. It just means that it has a very big core. Yeah. So there's something very bad here, right? That there's this factor of 10 discrepancy or more. And like I said, we haven't been able to measure the core binary fraction for all clusters. So I have plotted here a histogram of all the clusters in RC over RH. And you can see most of them here are pretty large values of RC over RH. But the theory only gets you up to this value right here. Let's see. I'm going to skip this. So the question is, why do clusters have such big core radii, right? What's causing them to be so puffed up? And one of the ways that you can get this is just by having another energy source at the core of the cluster, in addition to binary burning. And one of the things that has been suggested is that it could be that most clusters contain central intermediate mass black holes. And intermediate mass black holes act as an energy source, which would puff up the core. And Michele-Trenti has done some simple calculations that show that it gets you to just about the right value of RC over RH. The only problem with this is that we haven't observed a single IMBH ever. And the evidence that we have for them is tenuous at best. So there was an observation of M15 from the dynamics near the core that showed that there might be an IMBH there. But unfortunately, that went away when it was realized that the original authors used the wrong units on one of their axes. So there's another for Omega Cen that just came out recently. But Omega Cen is a very weird thing. It looks like it might be a strip dwarf galaxy. And there's yet another for G1 and in Andromeda. And the evidence there is not conclusive. It shows that there's a cusp in the velocity dispersion. It goes up as you get down to small radii. But it could equally well be fitted by just, you could equally well get that by just a bunch of compact remnants in the core. So it's not clear that there are IMBHs, although many people wish that there were. So another possible explanation is just that the initial conditions of clusters in our galaxy are not what people have traditionally considered. And that's kind of a boring explanation. Note that I said it, so hope just defending myself. So I'll kind of ignore that for now. Another is that you could have the evaporation of a stellar mass black hole subsystem. So what happens early in the evolution of a cluster is very massive stars. They go off the main sequence. They turn into black holes. And this black hole subsystem tends to decouple dynamically from the rest of the cluster. It sinks to the core, and you get like a subcluster of black holes. And these black holes kick each other out. And from the mass loss, this acts as an energy source that tends to puff up the visible core. And this could last long enough so that it would actually be observable. And this was proposed by Mackey in 2007. Another explanation, and this is something I'm working on with a student, is that when you have collisions of stars, so say you have two main sequence stars that are, say, one solar mass. When they smack into each other, they form a two solar mass star whose main sequence lifetime is shorter, right, than it would otherwise be. So you're basically taking your whole population of main sequence stars and you're expediting their stellar evolution mass loss. And what this does is that as soon as these stars become supernova, go supernova, mass is lost from the cluster, and it tends to puff up the core of the cluster on a time scale that's shorter than it would otherwise be without collisions. And this is something we're working on right now. Or it could be, and this is sort of the point that I'm laboring here, it could be that most clusters are just not in this binary burning phase. If you go back to this original plot that I showed right here, so I didn't mention what the units are here. It's TRH, half-mass relaxation time. But it could be that this initial phase, this core contraction phase, which is like the pre-main sequence phase in a star, is actually as long as the Hubble time. So instead of most clusters being in the binary burning phase, they could just be in this core contraction phase. And how do you test that? Well, we have a test. So as I mentioned before, it was suggested that by Verwundt and Hutt that these X-ray binaries that we see in globular clusters are formed through dynamics. And what they said, they had a very simple argument. They said that the number that you see, the number of X-ray sources you see in a cluster, should scale with the binary interaction rate. Right? So binaries are big things. When other stars come by, they tend to interact. And you can form new binaries in the process. And the way to write down, so you write down the interaction rate. You define it as gamma. That's what we've been calling it. It's a very simple thing to do. It's just a standard n sigma v type argument. where N1 is your single star density, N2 is your binary density. Sigma is some relevant cross-section. This is the relative velocity, which you can take to be the velocity dispersion. You integrate over the velocity distribution. And they approximated this by simply looking at the properties in the core. And of course, this goes as density squared, because it's a two-body process, times the core volume, which is the core radius cubed. And you have an extra factor of the velocity dispersion from the cross-section. So this approximate form is what's traditionally been used. And it's pretty decent, although it makes a few approximations. It assumes that all the interactions occur in the core, that the compact object fraction is constant among all the star clusters. But really the most important thing is that it only represents the interaction rate at the current time, right? And we know that X-ray binaries don't live forever, right? For LMXBs, they may live from 10 to the 5 to 10 to the 7 years if they have a giant donor, or maybe a billion years for a main sequence companion. And for CVs, the lifetime is roughly around the same. It's about 1 billion years. And in addition, so this is work that came out from Natasha's work. The strong binary interaction that makes something observable as an X-ray binary can have happened several billion years in the past. So in other words, the X-ray sources that we see now encode something of the history of the evolution of the cluster. Were actually, they were formed when the cluster was younger. So what does this mean? It means that the number of X-ray sources we see in the cluster shouldn't scale with the current interaction rate, but with the interaction rate integrated over some time in the past. So what I've done is I've defined a new gamma where I have the same n sigma v type calculation, the interaction rate. I just integrated over time. And you can simplify this as we did before. The main thing to note here is that you're integrating over some core properties, in this case velocity dispersion and core radius. You're integrating back. So T0 is the current time, so that's like the age of the universe, right? You're integrating back to some lag time ago. You're integrating over the X-ray, the typical X-ray lifetime, lifetime of an X-ray source. And what you can do then is you can plug in the 3 evolutionary phases of a cluster in here, in the core, right? And you can ask how many interactions occurred, which tells you how many X-ray sources you should see. So in principle, using the number of X-ray sources that we observe, we can distinguish between different states of evolution of these clusters in the recent past, right? So this is sort of a detail. We exclude the gravithermal oscillation phase because, as I mentioned earlier, there's only one binary there. And for most clusters, we see more binaries than that. So in the binary burning phase, I take the properties of the core to be roughly constant. For core contraction, we use some recent results from the literature. And the result that you get out is this. So if you take some cluster that you observe, right, and you don't know if it was recently in the binary burning phase or in the core contraction phase, but from this calculation, the ratio of the number of interactions in the binary burning phase that it had to the number of interactions in the core contraction phase goes like this expression. And I don't expect you to parse this, of course. But you should just know that it's a very well-behaved expression. So for a whole range of reasonable values for the X-ray lifetime, for the lag time, and for the current age of the cluster, this thing varies between a factor of 2 and 20. So in other words, if you're looking at some cluster, and if it were in the binary burning phase for the recent past, it would have 2 to 20 more sources than if it were in the core contraction phase in the recent past, right? And that's interesting because, where's my figure? Because these sources, these clusters, Tirzan 1, NGC 6397, and 7099, are overabundant by a factor of about 2 to 20. And there's no tuning that went in here, okay? I just plugged in some standard values. So that's very suggestive. So in addition to what we found from the N-body and Monte-Carlo work, this also suggests that, in fact, most clusters are still in core contraction. And it's only the few very overabundant clusters that are in the binary burning phase. So let me just sort of recap to try to tie this all together so it's clear. I see it as 3 different pieces of evidence that together form a nice self-consistent picture. One is that the clusters in the sample that the observers call core collapsed are overabundant in X-ray sources by a factor of 2 to 20, right? And then there's also this refined version of the gamma, the number of X-ray sources you should see, that I derived, that shows that clusters in the binary burning phase should have approximately 5. It's actually anywhere between 2 to 20. more X-ray sources than if they were in core contraction. And then there's also this business that I mentioned, comparing observations with theory, that suggests that only the core collapse clusters agree with predictions for the core radius in the binary burning phase. So when you take these all together, what it means is that only 20% of the clusters that we see should be, only the 20% of clusters that we see that are called core collapsed are actually binary burning, while the rest are still in core contraction. So that might not sound too exciting to you, but for people who have been doing this globular cluster stuff for a while, it's a big shift in thinking. So it means most clusters are actually like pre-main sequence stars, right? They haven't settled onto any sort of anything analogous to a main sequence, which is unfortunate because a lot of studies that are out there assume constant core properties with time. There's some calculations where people look at the number of blue stragglers that are formed, tidal capture binaries, which I mentioned didn't happen in nature, but in some rare cases they can actually be interesting. So all these studies, you can simply scale, as I've done here, but if you're interested in feedback properties where you're looking at perhaps the evolution of the binary fraction, a simple scaling may not work. Another thing that's interesting is, so if most clusters were in this binary burning phase, they would be like, like main sequence stars. And it turns out that clusters with a whole range of different initial conditions tend to approach common values of their structural parameters in the binary burning phase, right? But if they're still in this core contraction phase, they never approach that. So what we see now in clusters is related much more strongly to what they initially were when they formed, as opposed to just intrinsic evolution. And it's kind of anticlimactic, but a lot of the proposed explanations for these other cluster energy sources, like IMBHs and stuff, are just not needed, if what I'm saying is correct. Yeah?
What was special about these 20 globular clusters that allowed them to reach the binary burning phase?
Well, we don't really know what the initial conditions of clusters are. So it's a very difficult problem to go back. I mean, you can't evolve backwards, right? So what you do is you evolve from a whole parameter space, right? And you evolve and compare with what you see now to try to constrain the initial parameters. But because it's an expensive calculation, nobody's done it very systematically. So we really don't know what the initial conditions are for clusters. No, what I'm saying is we don't know the initial conditions of our galactic globular clusters. It could very well be that they just had longer relaxation times and just took longer to core contract.
So the ones that are in the binary burning phase just happen to have initial conditions that are short.
Yeah, they were just denser or something. Yeah.
But we saw that they weren't the most massive ones, right? Are they? I mean, could you observationally see if they're the densest ones?
Well, currently they are, right? But you can't tell initially because...
So currently they're the densest ones?
Yeah. But they're not the most massive necessarily. Yeah. So I've been talking about this for a while, and some other people have been talking about this too. We really need to do population synthesis of clusters. I know population synthesis is kind of like a dirty word, but we really now have the tools where we can try to do this systematically and try to figure out what the initial conditions are. We just haven't done it yet. So that's really the only point that I wanted to make. So just that globular clusters may be more immature, not by their age, but by their evolutionary state than we initially thought. And as I said, for people that work in the field, it's a big shift in thinking. So what I'd like to do now, and I realize I have 10 minutes left, but I promise I'll take less than that. I just want to talk a little bit about the work that I've been doing with the Monte-Carlo code. So all the stuff that I presented previously was all semi-analytical based on other people's work and observations and stuff. But I also do work with this Monte-Carlo code. And we've been playing catch-up with the N-body people. So the story of N-body goes back to the 60s. So this guy, Sfera Arsev, he's kind of like the grandfather of N-body. He wrote the first big N-body code that was popular, and he shared it with the world. Okay, and many other people have worked on it. They've added all kinds of physics to it, collision, stellar evolution, et cetera. But it's something that's been around for a long, long time. Monte-Carlo, on the other hand, is sort of a fledgling effort that was started by Michel Hénault a long time ago, but other people have picked up and sort of dropped after a few years. And the group that I work with recently picked it up maybe 6-7 years ago and have been working with it since. But because we have less manpower and we've worked with it for less time, we have less of the physics. And the last key remaining element was stellar evolution of the stars. Okay, and not just stellar evolution of the stars, but stellar evolution of the binary stars. Because, of course, this all feeds back. So your binaries are your energy source, right? And the rate at which they interact and how much energy they give up is dependent, of course, on the size of the binaries. But binary stellar evolution can change those properties with time, right? So this is a piece of physics that we needed to add. And we're almost done with this. As of a couple weeks ago, we have this guy, Jared Hurley. He wrote a very nice piece of code that does binary star and single star evolution. And we plugged this into the code, and it's nearly, so it's in the code, and it's almost working. And another piece of physics that we've added that sort of is there by default in N-body is some lost cone physics, in case you have a central black hole. And what the lost cone is, if people don't know what that is if you have a central massive object in your star cluster, what happens? So you have some central massive object, like a black hole in your cluster, right? And for some given radius, if you look at the velocity of a star, if the velocity is pointing exactly at the black hole, of course it's going to get gobbled by the black hole, right? If it's pointing exactly away, it still has zero angular momentum, so it's going to go out and come back in and get gobbled by the black hole. So those two lines form the center of the lost cones, right? If you have a velocity that's exactly tangential, it might be that you have enough angular momentum to not get gobbled by the black hole. So for every given radius, you have this thing called the lost cone. And whenever orbits go into this lost cone, these stars get eaten by the black hole. And this is something that was difficult for us to treat in Monte-Carlo because it happens on a shorter time scale than the relaxation time. But we now think we have it working. So let's see. So I don't really know the audience that well, and I've been just jabbering for like 50 minutes or 40 minutes. So does anybody want to see any of this stuff with the Monte-Carlo code? Does anybody like black holes or seriously? Because I've already made my point. I mean, if you're tired and you want to go, that's fine too. Yes. Oh, okay. Yeah, sure. Please. Yeah. Yeah. Yeah, than the other ones. Yeah. Yeah. Oh, yeah, so the reason simply is that these clusters, if you look back to their recent past, they're in this binary burning phase. So their density back, say, 5 billion years ago is the same density as what we see now. But these other clusters, they're still core contracting. So they look denser now, but they were coming from smaller and smaller densities in the past. So if you go back to when they formed, they might be these very loose, low-density things that are just still collapsing.
So they're actually denser now than
These? Yeah. Denser now than they were before.
So they're collapsed. I know their density is increasing during
Yeah.
Are they more dense than the ones than the outliers?
No, you can pretty much read off the density just from this. So as you go higher in gamma, the density increases.
So like 6366 is
Yeah.
less dense. I guess yeah, I'm trying to understand in terms of but it's not simply that the densest guys are in the binary burning phase.
No, not at all.
There are guys that are binary burning now that are less dense than guys that are so collapsing.
Yeah, so these three are binary burning, right? But this one, this Terzan 1, this gamma factor is 1. So it's not very dense at all. So it's very, very strange that it has 10 sources, right?
But that his density has been fairly constant.
Exactly, yeah.
The other guy, which is more dense now, in the recent past was less dense.
Yeah, say 63, 66, yeah. It's slightly more dense because it's further to the right. But
somehow he has more binaries or something, so he's able to reach the binary burning phase faster or something?
it could be that it initially formed with a higher density. It just took a shorter time, or it had a shorter relaxation time at the core. So there are several parameters which govern the evolution of these things that we haven't looked at.
The question is why if he's less dense than a guy currently, that the other guy still has not reached the binary burning phase?
It's all dependent on initial conditions. So it could be that this one just started with a much lower density than this one started with.
So if he's currently more, he's still collapsing has something to do with his current state. It
Yeah.
must be something about he has less binaries or something.
Oh, you mean why did this one stop here at this?
Why did he stop collapsing at a lower density than the other guy?
Right, yeah. So that could be related to the binary fraction. Yes, of course. Yeah. That's another thing that I didn't mention. I didn't go into the details, but this business about gamma right here, the symbol form that people use assumes a whole lot. And it assumes a binary fraction that's the same for all clusters. It assumes that the binary populations are all the same. Exactly as you're pointing out, they're not. Sorry?
You should divide gamma by mass to get a density, right? Gamma is not a density.
No, gamma is density. Well, I'm not sure I understand what you're getting at.
Before with the CVs, you were arguing that it makes more sense to use the small gamma.
Yeah, but that's only because there's a correlation, an observed correlation between encounter frequency and mass.
Yeah.
So if you want to try to get rid of that, you just work in specific units. Yeah.
Doesn't that make sense to do it for binaries too?
Yeah, I mean, you could do it, but I didn't need to in this case.
Oh, maybe, yeah.
Because you're just comparing, so you're just comparing gamma for two different evolutionary phases. Right? So you're just plugging in two different things right here. So you're dividing it basically by a different form of itself. So all this stuff out in front, which would include, 1 over the mass of the cluster, would just go away anyway. Because if you worked in specific units, all you would get is the ratio of this integral to itself for different evolving core properties. So that's one really nice thing about this is you don't have to work in specific units. I mean, it doesn't matter at all. Yes?
So is there any physical reason why you would expect the outliers to be nearly flat?
Yeah, that's a weird thing. I'm hoping I'm just unlucky. So you're right. There's 3 of them that seem to be pretty flat. So what are the chances? I haven't done the statistics of how likely it is that you see them all all 3 at the same curve. But I should say, so I'm hoping that I'm just unlucky, right? And there's not some other physics that I'm missing there. But Dave Pooley, so he's done a lot of these observations. He actually has a proposal right now that I think it's submitted as of right now, where he's going to look at a whole bunch of other core collapse clusters and see where they fit on this curve. So if I'm unlucky, there will be some straight line here, which means that there's something I totally don't understand. But hopefully, they're just scattered. We'll see. It should come out in the next year or 2.
When a binary is, these binaries are burning, when
Yeah.
they're exhausted,
Yeah.
is it that they've actually merged, or that they somehow the frequency has gone so fast that it's kind of no longer dynamically useful?
A few different things happen. So when you have a binary interact with another binary, what tends to happen is one binary gets tighter in the process, and the other one just gets disrupted. If you have a binary and a single, what happens is the binary tends to get harder. In other words, it gets tighter over time, right? But you can do a simple calculation, and if you look at the escape speed for a typical cluster, what happens is when the binary gets pretty small, eventually the recoil, the energy that it gives to the star and to itself, is so high that it gets kicked out of the cluster. The binary itself gets kicked out. So the star that it was interacting with and the binary itself.
They both get kicked out.
Yeah.
Okay,
Yeah.
yeah.
They both get kicked out. Yeah. And another thing that happens, and for main sequence stars this can happen a lot, is you just get mergers. So you have binary interaction and a bunch of stars merge, and that's another way of destroying binaries. Yeah. So I think I'll skip, my time is up anyway, so I'll skip all the stuff at the end. And my summary is just what I've said before. We have these 3 independent pieces of evidence, and they suggest that most clusters are still in core contraction, which is weird. And I didn't talk about the Monte-Carlo code, but hopefully in the near future you'll be seeing a whole lot of exciting papers that will be done based on it. So thanks for your time.
You can at least, I guess, very vaguely reverse your logic and say, what do you need for the initial thermal relaxation time to be of order half the Hubble time, which I guess this implies, or maybe almost the
Yeah.
Hubble time actually.
Yeah.
So is that a density is that a crazy density, or is
No,
it
it's not crazy at all.
I see. So it's
Yeah.
basically, isn't this comparable to, say, Orion, or?
Oh, I don't know the exact numbers. I haven't looked at it. Because there are a few other factors as well. So there's tidal stripping. If your cluster is big enough, it'll be stripped by the host galaxy. So there are a few other factors that come in, but we haven't done the calculation.
Okay,
But
not crazy, that's all.
no, it's not crazy at all. No.